Let's continue our discussion on unsupervised learning, and we're going to focus on Gaussian mixtures. Apparently, Gaussian mixtures is something very much different from what we discussed so far, like k-means or db-scan. Let's see what is Gaussian mixtures. Gaussian mixtures model also stands for GMM, is a probabilistic model that assumes that the instances were generated from a mixture of several Gaussian distributions whose parameters are unknown, hence the name of the methodology, GMM. So every single instance is generated from some distribution, and these distributions happen to be Gaussian, and then you just don't know their parameters. Okay, so the dataset X is assumed to have been generated through the following probabilistic process. Let's look at the algorithm. For each instance, a cluster is picked randomly from among k clusters, and the probability of choosing the G cluster is defined by the cluster's weight, phi j. And the instance of the cluster chosen for the ith instance is noted as the index of that cluster is chosen is called zi. So if it happens that zi equal to j, essentially says that ith distance has been assigned to the j's cluster, a specific cluster. Then remember, if you look at the previous one, we said phi j to define the weight. And then once you assign that, it essentially says that phi j is really big, right? For this j's cluster, for this ith instance. And then the location of this xi of this instance is sampled randomly from the Gaussian distribution with mean mu j and covariance of sigma j. This is noted as xj is sampled from normal distribution with mean of mu, with sigma being at j's cluster. So that's Gaussian mixtures. Let's look at the graphical representation of the whole process. So in this chart, you can see that it has specific explanations on the left-hand side. Let's go through one by one. The circles represent random variables. So you have xj and zj. And then the squares represent fixed values, parameters of the model. So the Gaussian distribution parameters mu j and sigma j. And the large rectangles are called plates. Those two are considered to be plates. They indicate that their content is repeated several times. Because you have multiple observations, you have multiple clusters, so you have this repeating of each one of them, assigning or labeling process. So that's why it has, it's called plates. And the number at the bottom right of each plate indicates how many times its content is repeated. So in this case, we have m random variables, zi from z1 all the way to zm, and m random variables of xi. They are also k-means because you have k clusters, which associated with k-mu's and k-sigmas. And each variable zi is drawn from categorical distribution of phi, which is the weights. And then each variable xi is drawn from that normal distribution with the mean and covariance matrix defined by its cluster zi. In addition to this, on this chart, we have something else, like the solid arrow and the squiggly arrow. The solid arrows represent conditional dependencies. For example, the probability distribution for each random variable zi depends on the weight vector phi. And also note that when an arrow crosses a plate boundary, it means that it applies to all the repetitions of that plate. For example, the weight vector phi conditions the probability distribution of all the random variable x1 to xm. That's essentially outside, right? From here to there and from here to there. A squiggly arrow from zi to xi represented a switch. Depending on the value of zi, the instance xi will be sampled from different Gaussian distribution. Essentially, because different clusters have different parameters, it would sample from different different distributions. And on top of that, one more thing, shaded nodes indicate the value is known, so that in this case, only the random variable xi have known values. They are called observed variables, and the unknowns are called latent variables. The weight itself is a latent variable, but the instance itself are observed variables. Okay, I know it's somewhat hard to understand. Read through this multiple times with the hope that you would understand it better. So let's see how we can implement Gaussian mixture in scikit-learn. It's rather simple. You can import a class of Gaussian mixture, and then you can define the number of components equal to 3. And let's see what it meant, right? This very similar to k-means. It will have 3 clusters, and each one have the corresponding centroid coordinates. So that would be those 3. And then it have covariances of this Gaussian mixture. So this one actually leverages something very similar to k-means. And then this approach is called expectation maximization. This algorithm is actually very famous, so you should definitely know it. So what it does is doing very similar to k-means, but with slight change in one of the steps. So let's take a look at this in detail. It initializes a cluster of parameters randomly. First, assigning instances to the cluster. This is called expectation step. You can see that the first 2 steps are very much similar to k-means, right? And then updating the cluster. This is called maximization step. It's the same as k-means as well. It actually do have some difference here. Let's take a look at the last bullets here. It is more generalized clustering algorithm, not only estimating the mean, but also the size, shape, and orientation. It is a soft clustering algorithm. So what it does is this assigning to cluster is not hard clustering. It doesn't mean it would go to a specific cluster 100%. It assigns with certain probability. That is a difference from k-means. It is a soft clustering with a probability attached to assigning a point to all the different clusters. So in other words, one instance would have 3 in each step, or in each iteration, it would have 3 probabilities attached to it, which is corresponding to different probability that it should be assigned to different cluster. As you can imagine, those 3 probabilities should be summed equal to 1. That's the only difference. That's the key difference between expectation maximization algorithm versus k-means. So let's continue and take a look at this Gaussian mixtures in scikit-learn. You could predict. So here, how to digest this, right? You have a bunch of you have a data input of x of instances, and then when you predict, it belongs. Each one of them belongs to a certain cluster, 0, 1, or 2 in terms of index. For example, the first observation, it is predicted to be cluster 2. But if you look at the predict probability, you would see that it actually have 3 probability attached to it. Probability of being cluster 0 is 0.02, and being cluster 1 is really, really small. But being cluster 2 is around 0.977. That's why this one, first observation, is labeled as cluster 2. How about second observation? Let's take another example. Apparently, this probability is larger as well, which happened to be cluster 2 as well, right? So that's how you digest the output from scikit-learn. So let's look at what's on the right-hand side. You have some new samples, and then these are the values of the new samples. And then let's see how you could you actually can generate, you can leverage Gaussian mixture to generate samples. In this case, you generate 6 samples, and then these are the corresponding x new coordinates, and then the corresponding y new cluster. Okay. You can also leverage Gaussian mixture to understand the PDF of the cluster distribution. So what this does is you can see that it shows the cluster means, the decision boundaries, which are the dashed red lines, and also the density contours of this model. You can see that, okay, this one is one of the clusters, and within the cluster, you can have the density contours of the model. So that's something that you should be aware. And then there's some other special types that you should pay attention. That is, if you change your covariance type equal to tide or spherical, it shows apparently different results than what you have initially called covariance type being ellipsoid. And then Gaussian mixtures are doing very well on the ellipsoid type of data set. And then we can leverage Gaussian mixtures for anomaly detection. Anomaly detection is useful in a wide range of applications. As examples, you could detect credit card usage fraud. So in fraud detections, you could use Gaussian mixtures. You could detect defective products in manufacturing, another possibility, or removing outliers from a dataset before training another model. So essentially, you want to identify outliers, anomalies. If you could remove them, you could significantly improve the performance of the resulting model that you already have some experience, I assume. So let's see if you define a certain percentile. In this case, in this example, you labeled 4% of your data being anomalies. And then once you have this cluster algorithm working, Gaussian mixtures clustering algorithm working, what comes back would be some of the data points, which is labeled as a red star, are considered to be the outliers or anomalies. Either way you think through them. And then you could do one more thing. You could remove some of these outliers, try to enhance your whatever follow-up algorithms that you are going to test upon this data set. In here, same thing. You need to figure out what would be the proper number of clusters. The two metrics that you use are called BIC and AIC. If you look at the function form of BIC and AIC, they are actually somewhat connected. So they have some specific relationship here we actually didn't discuss, but just keep in mind that they're essentially the same thing. So in these equations, you look at all the parameters. M is the number of instances, as we discussed earlier. So essentially number of observations. P is the number of parameters learned by the model. And L is the maximum value of the likelihood function of the model. And then just be aware, both of those two parameters or metrics, we should see more precise. The metrics BIC and AIC penalize the more complex model. We would have some sort of graph very shortly, but so far let's look at the definition of likelihood function. So likelihood function itself is given a x observation, what is your parameter theta? So if you have a given value of 2.5 that you know, x being 2.5, what's your likelihood function of your theta? And in this case, you always want to find the maximum likelihood function of the theta, which will give you a corresponding value. And then on the bottom right, you saw it's just the log likelihood of the same function that we saw on the top right. And then on the bottom left, this chart is really the PDF, which is theta is given what is your distribution of x. Theta is given as 1.3 in this example, which is a black line. And then what's the corresponding distribution of x? So when we leverage BIC and AIC, what you do is you want to find the minimum value of AIC and BIC. As I mentioned, both of them there's some mathematical relationship between BIC and AIC, so that they are representing almost same thing. That's why their shape of AIC and BIC are very similar. You can see here, if you look at the minimum value of BIC, you would come back with a conclusion of 3 clusters. And the same thing for AIC, the 3 cluster results in the minimized AIC. Let's look at something beyond Gaussian mixture models. It's called Bayesian Gaussian mixtures. Bayesian Gaussian mixtures is capable of giving weights equal or close to 0 to unnecessary clusters. So in this example, you can see that if you have 10 clusters, and then turns out that the weights for majority of them become 0. Only 0.4 for one of them, 0.21 for the other one, and 0.4 for the third one. So that's Bayesian Gaussian mixture models. And then here, just graphical view of Bayesian Gaussian mixture models. It really have some new inputs that you should take another look. That would be the D and the V, and even something called prior. So let's look at what is prior. So prior knowledge about the latent variable Z can be encoded in a probability distribution PZ that is called the prior. And then if you have weight concentration prior equal to 0.01, you come back with what we saw on the left-hand side, versus if you have weight concentration prior equal to 10,000, you saw what's on the right-hand side. So that concentration is really determining how this contour plot would look like. And then because of that weight concentration prior, it actually gives you the different results. And the question becomes, how can you figure out this prior, right? It's really some knowledge or some information that you know about the data can as an input or as a prior to help you to continue to digest the results, digest the model output, or digest the whole process. So you have to specify some sort of prior in your model. So here, from the Bayes theorem perspective, let's look at what is that prior, right? The prior essentially is this PZ, probability of Z. So in order to figure out the probability of Z given X is the observation, the data, that's called posterior probability, just because you have observation of X, which is the data, and then you want to figure out the probability of Z given X. And then this can be computed by the likelihood, that is probability of X given Z, given a specific parameter. Remember that we said if the parameter is already null, and then look at the distribution, then it becomes the likelihood, right? So you use px given z times pz. Pz is a prior divided by px. This is a Bayes theorem that you should already know, that shows you the relationship between prior and posterior. So something that you already know about this z parameter. And then turns out that the evidence of px is often intractable, just because we need to do this integration among all possible z's. So as a result, we leverage something called KR divergence. And what it does is, by all this mathematical manipulation, it's actually simple. Just use log, minus and plus kind of thing, and then essentially says you could come back with estimation of this quantity, the difference between log px and ELBO, to figure out the KL divergence. That is also leveraged in this whole Bayesian process, in the Bayesian Gaussian mixture process. So let's look at some specific pitfalls, or the ones that is not going to do well in the using Gaussian mixtures. Gaussian mixtures actually would be doing really well on ellipsoidal type of shapes. So if you recall one of the example that we discussed in dbScan, so those type of ellipsoidal clusters, you would not be doing well using dbScan, but Gaussian mixtures can do a decent job there. However, for non-ellipsoidal clusters, so before we move on to that, right, what is exactly ellipsoidal clusters? It would be something like this, right? And then if you have this type of shape in a Gaussian mixture, it would be perfect for you to look for the pattern. But in this case, it's not. It's non-ellipsoidal, because all the data is not kind of following. If this is doing that, then probably you could see it's ellipse order. So that's why in this case, if you apply Gaussian mixtures onto the data on the left-hand side, what happens is you see this weird structure or boundary of your Gaussian mixture output, and then it just doesn't work. So you have to pay attention to what would be the proper methodology that you want to pick and choose. In addition to this, just want to remind you that there are all kinds of other ways or algorithms for anomaly and novelty detection. So anomaly, the way that you look at it as an outlier, or in certain cases, when you want to define novelty, you can leverage novelty detection as well. So other algorithms here you should pay attention to in the future as well, such as PCA, fast MCAD, minimum covariance determinant, isolation forest, local outlier factor, and one class SVM. And these are the methodologies potentially you could leverage. And here we do not elaborate as much. Okay, I'll stop here and thank you.